So today we're going to talk about friction. So just some definitions for friction. There are two main types of friction, static and kinetic. So static friction is, of course, friction when an object isn't moving relative to another object. So for example, a book isn't moving on a table. So static friction isn't consistent. It will have variable magnitude. It will be equal to the applied force until it's overcome. And the applied force can be variable. So if you, say, for example, are trying to pull that book along the table, then the force of friction, as you increase your force applied on the book, pulling it along the table, the static friction will increase until the book starts to move as the force that you're applying to the book increases. So it is variable, and you can see that in the Freebody diagram if you were to draw one. And then there's kinetic friction. So this is friction during sliding. So again, with a book example, if you are sliding a book along, there's some friction, there's some drag between the book and the table. And this is given as the force of kinetic friction is equal to mu k n, where mu k is the coefficient of kinetic friction. This is unitless, and n is the normal force of the object, which is measured in newtons. So direction of kinetic friction, the force of kinetic friction, is opposite to the motion of the object relative to the surface. So if you're pulling a book along a table to the right, then the kinetic friction would be towards the left because it is working against you. So some special cases for friction. So impending slip will happen when the static friction is equal to the maximum static friction. So the static friction cannot exceed Fs max, which places an upper limit on acceleration. So Fs max is equal to mu Sn, really similar to the force of kinetic friction. Also note that it is possible for objects in contact to lose contact after static friction is overcome. This is because they have, especially if they're different masses. So if they're different masses but the kinetic friction is the same, then, or the coefficient of kinetic friction is the same, then one will move with greater acceleration than the other, the one that is less massive. And then we just want to use the same force analysis techniques that we went over in the last video to solve for forces of friction and related acceleration. So for a video example, we have a pulley system that we want to calculate the acceleration of if it is released from rest. So you can see there are two blocks there, block A, block B. My apologies. It's not drawn terribly well, but it's what we have to work with. And block A is on a 30-degree incline, block B is on a 60-degree incline. The mass of A is 12 kilograms, mass of B is 10 kilograms, and the coefficient of kinetic friction for both A and B on the surface is 0.4. And for this example, we just want to assume no static friction. We'll go over whether you use static friction or kinetic friction sort of in the extra example where we want to determine the force needed to overcome the static friction. So then you can find out if you want to use static friction or kinetic friction on a problem. But for now, we'll just stick with this. So again, we'll assume no static friction, but we want to use the same techniques that we used in the last video. So that is drawing a free body diagram, kinetic body diagram, finding those equations of motion for each object, and then using kinematics and manipulating the equations. And for this example, we'll see that it doesn't need very complex kinematics. So first of all, I'm going to draw a free body diagram and kinetic body diagram for A and B. Okay, so A is, this is what A looks like, the block or the box or whatever it may be. So we know that it's connected to the pulley So this will cause tension. We also know that it has mass. So this will be the force of gravity, which is mg. And because the incline is 30 degrees, so just a reminder that that is 30 degrees. So this should also be 30 degrees there, that angle there. If you imagine, tilting that box, then that should be 30. And then, of course, it has a normal force as well. And it will have a force of friction, but we don't know where the force of friction will be acting in. I'm going to assume that the box will be traveling in this direction. So that means that the force of friction is here. So that's just FF is force of friction. And if we find out that that's not the case, and in fact it's traveling the other direction, then we'll just get a negative force of friction, negative tension, etc. So this is equal to our kinetic body diagram, which is this, mass times acceleration. And we can treat the box as a point. So then for B, we'll do the same thing. So B, we have a box on a, oops, that's probably too steep, but it is on a slightly steeper incline. Again, we have our tension, and because it's an ideal pulley, this tension will be the same as the tension in A, so I didn't use any subscripts because they will be the same. And then we have, again, our mass times gravity, our gravitational force, and this will be 60 degrees, that angle there. And we'll have a normal force which is perpendicular to the surface. So we can call that normal B. And then assuming that the direction of motion is this way, then we will have a friction force here, which is opposite of the direction of motion. And again, if we're wrong about our assumption that the friction force is that way and that the direction of motion is up in this case, then we'll just get negative numbers and we'll just have to kind of change what we're doing there. So this is equal to, again, treated as a point source, and then mass times acceleration. Okay, so we have our free body diagrams. And now we want to find our equations of motion. Okay, so for this, I'm going to choose a tilted coordinate system for both A and B. So for A, I'm going to have one component be along the surface, and I'm going to say that's positive. So it's kind of like splitting it up into X and Y components, except we'll have one component which is on the surface and one component which is perpendicular to the surface. So this component will be, so if we go back up here, the component going sort of down the slope will be mg cos 30, because we want this part here, and minus t, because tension is going up, and then minus mu k na, minus the friction force, which, yeah, again, is that mu times normal force. So I'll just write that down. So the force of gravity, and then cosine of 30 minus T, tension, minus mu K N A. And that is equal to mass times acceleration, which is in our kinetic body diagram there. And then for our other, so it'll be perpendicular to the one that we just drew, and I'm going to label that as positive. So then for that, we have, oops, I forgot to label that. There we go. So we have NA in one direction and mg sine 30 in the other. No, sorry, mg cos 30, because we want sort of this part of it here. So that would be cosine of 30. So I'm just going to go and change that in here, because that should be sine. Yeah, okay. So we have mg cosine of 30, and then that would be negative because it is going down compared to our coordinates here. So you can see, up here, that would be downwards. And then the opposing force is our force of our normal force. So we can say plus normal force of A. And that is equal to 0 because there's no motion in that axis. We can see that it's purely in, from the kinetic body diagram, it's purely in this axis here, which is along the surface. Okay. So for B, we'll do the same thing. I'll go a little bit quicker. So I'm going to choose my first axis along the surface, and we don't need to use the same coordinate system for both, but we can see that positive would be T, negative would be mg sine 60, and the force of friction would also be negative. So we have T minus the force of friction, which is mu K N B, minus mg cos, sorry, that should be sine of 60 equals mass times acceleration, which is our kinetic body diagram there. And then our other coordinate, perpendicular again to the surface and to our last coordinate, and I'll make that positive. You can choose whatever you want though. And similarly, so we'll have the normal force of B minus mg cos of 60. Let's make sure we've got that right here. Okay. Cos of 60 will give us this, which is what we want. Okay. So then we're ready to manipulate some of the equations, and I'm just going to say that's equal to 0. So manipulate equations. Okay. What I'm going to do is I'm going to sum this equation here I'm going to label it 1. And this equation here, which I'll label 2, so this will act to eliminate t. So, oops, I'll say 1 plus 2 equals, all right, what do we have here? So we have mg sine 30. And I should have had the subscripts here. So mag sine 30. And then minus t minus mu k and a. And then we have plus t minus mu k and b minus mb g, that would be cos. Sine, that would be sine. 60 equals, and then I'll just put g m a plus m b. So simplifying a little bit, we can see that the tensions cancel, which is what we wanted, because we don't know the tensions. And then I'll just write this out. So and then NA we can get from this equation. So if we bring this part over, then we have NA is equal to mg cos 30. And then minus mu k. And similarly, it would be mb g cos 60 minus mb g sine 60 equals, and sorry, that shouldn't be g, that should be a plus m b. So then we can put some of our numbers in here. So I'm just going to use a calculator to sort of skip some of the intermediate steps, but you know where they're coming from, just based on the equation above. So we have MA being, let's see what it is here, 12 kilograms times 9.81 times sine of 30. So I get 58.86. We'll worry about sig digs later. And then mu k was 0.4. So 0.4 times 12 times 9.81 times cosine of 30 equals 40.78. And we have minus 0.4 times 10, which is the mass of B, times 9.81 times cosine of 60, which is 19.62, minus MB, which is 10 times 9.81 times sine of 60, which is 84.95. 0.96 if you're rounding, equals a times ma plus mb is 10 plus 12, which is 22. So simplifying a bit more, I'm just going to add up all the things on the left. And divide by 22. So negative 3.93 is our acceleration. So that just means it's negative. So we assumed that acceleration was going to be to the left, but in fact, B would slide down and A would slide up. So that means acceleration is 3.93 meters per second. We can say right. So B slides down, A slides up. So that's how we use our procedure for forces. We had to draw a free body diagram and a kinetic body diagram, find those equations of motion, and then use those equations and manipulate them to solve for the acceleration. And that is it for today's video. I hope you enjoyed. Again, the extra example will be in the description below, as long as the annotated version of this and the PowerPoint. Thank you again to my professors and to Loom and Google Keep. And thank you for watching. I hope this helped.